Well, take the Earth. The rotation axis of the Earth does not coincide with the magnetic dipole axis because there's about 10 or 15 degrees difference. It's somewhere in northern Canada. There's almost no astronomical object that you can think of whereby the axis of rotation coincides with the magnetic dipole axis. It's very rare. Of all the planets in our system, there's only one planet whereby they are aligned. So it is very common that they are not aligned, and so this idea of pulsars, that it is a misalignment between the axis of rotation and the magnetic dipole axis, is generally accepted. If somehow that beam misses the Earth, well, then you don't see the pulsar. So there are way more pulsars in the sky than you can see. You only see the ones which happen to have that narrow light beam, radio beam, in your direction. So now we go to the Crab Nebula. Next slide. So here is the Crab Nebula. This object is at a distance of about 6,000 light years from us. From here to here is about 11 light years. The neutron star is this one. That's the star that exploded in 1054. The white light that you see, we give that a name, we call that synchrotron radiation, which is the result of electrons moving around magnetic fields. But the blue light that you see are the filaments, which is the original matter of the star when it exploded and threw this matter out in all directions. It runs out with about 10,000 kilometers per second. And so this is the original matter of the star. If I put the moon on this picture, then the moon would be 6 times larger in angular size. But of course, this is at a distance of 6,000 light years away from us. The next slide shows you a galaxy. The galaxy has, of course, a name, like all galaxies. This one has the name NGC 5253, 10 million light years away from us. So the light that you see here was emitted 10 million years ago. And here you see a supernova in that galaxy. And this star alone emits about the same amount of light per second as the entire galaxy. And a galaxy holds roughly 100 billion stars. And so that supernova alone outshines 100 billion stars. And you see it here a few months later, again a few months later, and again a few months later. It's about a year between this picture and about this picture. And so it's not too surprising that the Crab Nebula, which is relatively close, that it was visible even during the day. So we've talked about neutron stars and the incredible injustice done to Jocelyn Bell, and now I will turn to black holes, so if we can get the lights back up again. Can we get more lights? A white dwarf has a maximum, 1.4 solar masses. If it's more massive, it collapses into a neutron star. A neutron star itself has its own limit. That limit is not so well known as it is known for the Chandrasekhar limit. It's roughly 2.5 to 3 times the mass of the sun. So if you take a neutron star and you keep piling up matter, if it becomes more massive than 2.5, 3 times the mass of the sun, it will collapse. The collapse will never stop. And the size of the star will become a point. 0 size. We call that a singularity. We call that a black hole. It's unimaginable. The density of that point is infinitely high. There is 3 solar mass in that one point, and that point has no size. So it's totally unimaginable what a black hole actually is. our knowledge of physics is insufficient to deal with singularities. It's lacking in physics to deal with objects that have gravitational fields which have the size of a point. However, what we do in physics, we define what we call an event horizon. An event horizon is a sphere around the black hole. I'll make a drawing of the black hole is the point. And there's here a sphere. And I'll give this sphere a radius r. And this sphere is called the event horizon. And as long as you are outside the event horizon, you could go back to Earth. If you're inside the event horizon, you can never return to Earth. You will always end up on the singularity on the black hole. The reason is that when you're inside the event horizon, in order to make it back to Earth, you would need a speed larger than the speed of light, which we know is not possible, so you're trapped forever. So the event horizon is an enormously important surface in astronomy. And the event horizon can easily be calculated. It was done by Schwarzschild first. That's why it's often called the Schwarzschild radius. R equals 2 times capital G, I will tell you in a minute what that is, times m divided by c squared. R is the radius of the event horizon. G is the gravitational constant that you can look up in any book of physics. M is the mass of the black hole, and c is the speed of light. Notice that r is linearly proportional with m. So if you make the black hole twice as massive, the event horizon becomes twice as large. It's scaled strictly linearly. To give you an idea, if the black hole had a mass of 1 solar mass, suppose you could make one, then the radius would be 3 kilometers. So a black hole of 10 solar masses would have a radius of 30 kilometers, 10 times more. If you take the Earth and you take a vise and you make the Earth smaller and smaller and smaller and smaller and smaller, if you get the Earth back to 1 centimeter, it will become a black hole. So the event horizon of an object like the Earth, if you could make it small enough, would be 1 centimeter. How were black holes discovered? In around 1971, 1972, a new kind of object was discovered in the sky, which has the name of an X-ray binary. Let's take a look at the picture and look at an X-ray binary. If you can make it a little darker, that would help. The word binary already tells you that there are 2 stars. Here you see a star, which is a normal thermonuclear star. Could be a star like our sun. It might be 10 or 20 times more massive, but it is a normal thermonuclear burning star. It's alive. It's not dead. It hasn't used up its thermonuclear fuel yet. If it is in orbit, this is a binary system, with a very small object, for instance, a white dwarf, or a neutron star, or, as you will see, a black hole, and if they are close enough to each other, it is energetically more favorable for the material from this star to fall towards what we call compact object. We call therefore this star the donor, it gives matter, and we call this star the accreter, it accretes matter. Since this going around in a orbit, the matter cannot fall radially in, but it spirals in, and it forms therefore what we call an accretion disk. These objects were discovered in around 1971, 1972. Let us for now assume, for the moment, that this were a neutron star. And so matter would fall onto the neutron star. if you ever had your first course in physics, you've learned about Newton's laws of gravity. And you can calculate with what speed an object would hit the surface of the neutron star. It's really a trivial calculation, and the answer is it's about half the speed of light. An enormous speed with which it hits the surface of the neutron star. To give you a little bit of respect for what it means that an object hits the neutron star with half the speed of light, do you in Spain know what marshmallows are? You do. You do know what marshmallows are? I have one here. 5 grams maybe, at most. Yeah? If you throw this marshmallow from that distance onto a neutron star, then the energy that is released, gravitational potential energy, is converted to speed. The energy that is released is comparable to the bomb thrown on Hiroshima at the end of the Second World War. Just a marshmallow throwing onto a neutron star hits the star with half the speed of light.